Hello, and welcome to Beginning C++ Programming. This week we're going to be talking about pointers and structures, kind of some miscellaneous stuff that is kind of unique to C++ programming. But as we begin to sort of on-ramp our way towards object-oriented programming, which will be the focus of the second half of this course. So let's start with pointers. So what is a pointer? In a lot of classes, especially beginning computer programming classes, pointers become very, very complicated, and people make them very complicated. So I want to make this as simple as possible and not get into all of the sort of nuance of what you can do with them until you feel more comfortable with them. We'll talk about a few applications, but yeah, let's not make things confusing. So what is a pointer? A pointer is just like a variable like any other, but the thing that it holds is not a value, it's an address. They are variables that hold addresses. It's really simple. And so I kind of can show you some different examples of this, but one of the ways you can get to the address of a variable, there's actually another operator. It's the ampersand operator or the at operator, or not at, but it shows you the location where that variable is at, right? And so here I'm printing out, I have a variable in, like any other variable we've ever created. And then I can just print out, the value or the place where in is stored. The in stores its value at, and then I just print out ampersand in. If you do that in C++ right now, it will give you the address where in is located. And that will be different maybe every time you run it. Although if you run it back to back, often it's the same time, or same location. But still, maybe it'll be different the next day, depending on what you have running on your system. Like it's just the actual address on your computer where that variable happens to be located right now. And so, yeah, you want to get the address of something, put an ampersand in front of the variable. It'll tell you what the address is. Now here's the thing, we're talking about pointers, so what I want to do is actually store that address. And so what I can do is I can create a pointer. So now pointers in C++, and by the way, C++ is one of the few languages that will actually give you access to pointers. Java seemed to be actually like purpose written to get rid of pointers from day-to-day programming tasks. Like, it's just the way it's done. And so here we're going to create a pointer, but a pointer has to point to a specific type. So you can't just create a generic pointer. It has to be a pointer that's pointing to something. And then C++ chose to use a syntax that, if I'm honest, not my favorite, for a couple different reasons, one of which is that this symbol is going to get reused. But we use the star operator in order to declare a pointer. And you put it like sort of in front of the name of the pointer. So here I've got int in, right? So in on the screen right now is an integer. That is its type. P is a pointer to an integer, right? It's an integer pointer. And that star sort of represents, like this is a pointer to something. You can actually, by the way, put the star on the int, but in general, we put the star on the name in case you're doing things like back to back. If you're going to declare 3 integer pointers, you would say int star p, star q, star r, whatever you're going to call them, right? But you put a star on each name. So that's how you declare a pointer. So what are you going to put in the pointer? Well, an address. So here I have p just storing the address of in. Granted, there's lots of different ways of getting an address. We'll talk about one in a little bit later. But right now, I just happen to have a variable with an address, so I'm going to stick the address there. So now what's the value of p? The value of p is whatever address in is located at. Now, by the way, p is also a variable. Pointers are variables. They actually take up memory themselves. There is an address for p. And this is where people start making things confusing. What about a pointer to a pointer? Oh, absolutely. You could have a pointer that points to an integer pointer. So that would be int star star q, right? Don't do that. Why would you do that? I mean, I'm sure there's going to be a situation in which case that might be necessary, but it's certainly not the standard case, and it certainly isn't something we need to talk about today. Point being, don't make things confusing. A pointer holds an address. Keep it simple. Here it's got the address of in, wherever the value of p is wherever in is located. Now, how do you get the value of a variable from its address? That's where you dereference. And unfortunately, C++ chose to use the exact same symbol you used to create a pointer to dereference a pointer, even though they're different operations. So here I'm printing out the value of n is, and that, second to last line, star p. So the first star p is where we're declaring that pointer, right? We're saying that p is not an integer. It is a pointer to an integer. After that point, anytime I use star p is going to go to that address and dereference that value. So in other words, I'm going to not give you the actual address. Like if for that first line, right, I'm printing out p, that's going to give me an address, the location of wherever n is. But when I do star p, I'm going to go to that address and it gives me whatever value is at that location. So star p is going to print out 17. P is the address where n is located. Star p is 17. It's go to that address and give me the value at that address. That's a process called dereferencing, and unfortunately, it uses the exact same symbol that we used to create the pointer. Maybe that's helpful, maybe it's confusing, I don't know, but I think other languages make it a bit easier. So let's just kind of do some referencing here. I've got n has a value of 17. It's located at an address that ends in 42. I've got p. P holds that value, holds that address. The value of p is the address that ends at 42. Now p happens to also be located at the address that ends in 54. I know these are hex numbers, but close enough, right? So this is my structure here. So if that's the case, what's the value of n? Well, the value of n is what the value of n has always been. It's 17, right? But what's the value of ampersand n? Ampersand n is the address of n, which is the address that ends in 42, right? It's wherever n is located. So what's the value of p? Well, we just set the value of p to the address of n, so p is the exact same number. P holds the address where n is located. But what about star p? Well, that's dereferencing p, which means p has an address. I'm going to go to that address, and then I'm going to give you the value of the variable at that address. That would be 17 again. By the way, what's the value of ampersand p? Ampersand p is the address that ends in 54. It's the place where p is located, because p is a separate variable. It takes up memory. It has a slot somewhere in your RAM for it. Now, why do we care about pointers? How are they useful? And how are they connected to functions? So we talked about last week with functions that when you call a function, you're sending an argument. That argument is assigning a value to the parameters of that function before it starts running. But what are you actually sending? And this is sort of the reason why we're bringing up pointers right after functions. So C++ by default is pass by value. That term means that when I call a function and I send an argument, what I'm doing is I'm evaluating whatever the value of that argument is, right? If it's a variable, if it's an expression, whatever it is, I evaluate that, and then I copy that value and I assign it to the parameter. That works fine for most things. If you're trying to multiply two numbers together, if you want to calculate the tax on a particular item or something, right? If I just copy the value, you can give me the correct answer. You don't need access to the original value. In fact, maybe I don't want to give you that. Like when I pass you a variable to a function, I don't want to give you access to that original variable. You could change it. Like what if your function ends up changing my value and I didn't want it to be changed, right? So pass by value is the default. So let's look at this code. This code is attempting to create a function that performs a swap, right? It just takes one thing and swaps it for another. You can see that I've got the function prototype or the function declaration at the top, and then the function implementation or definition at the bottom, right? So what does swap do? It takes two integers, a and b. It creates a temporary integer because if you think about the way that you work with like assignment operators, it's kind of impossible for a computer to like pass things back at, like, you can't do two things simultaneously, right? So you can't kind of juggle them, like throw them up in the air and grab them, right? If I take B and I, put it into A, then I lose the value of A. So I've got nothing left to put back in B. If I take this one, I put it in this one, then I lose B and I don't have anything to put back into A. So the way that you have to do it is you sort of have to have like a table, right? It's like, hey, I need to have another surface or another hand and say, I've got A and B. I'm going to create another hand called temp, and I'm going to take the value of A and I'm going to put it into temp. Now I haven't lost the value of A, but now I've got it stored over there in temp. So what I can then do is take B, assign that to A. So now A is gone. I've got B and B, but hey, that temp still has the value of A, so I can take that temp and put it into the value of what used to be B, and now I've got A and B. Hopefully my hand signals made sense. But point being, you can't just flip two things at once. You have to sort of place one somewhere while you make the swap and then pull it over. So that's why we create a temporary value. We store the value of A there. Then we set the value of A to whatever B was. Now A and B both have the same value. But then I take B and I set it to whatever my temporary value was. So it has the old value of A, and now I've effectively swapped the two. That's kind of how you would do it. The problem with this function is, what am I actually sending? You see in main, I've got 0 and 1 for x and y. And then I call swap xy. But what I'm actually doing is evaluating those two variables. I'm not sending you the variable x, right? I'm sending you 0. X evaluates to 0, and so I'm taking 0 and I'm copying that value into A. I'm taking y, which has the value of 1, and I'm copying that into B. So when you print it out, nothing changes. I'm actually swapping two variables inside the swap function that are not at all connected to the two variables inside of main. They just happen to have the same value for a second before we made the switch, right? I'm passing a copy. That swap isn't actually doing anything. So then, what if I want it to actually do something? What if I want to give you the ability to edit my variables or my objects or my, well, we haven't got to objects yet, but eventually we're getting there. So what I want to do then is not pass by value. I want to pass by reference. In other words, I don't want to pass you just the value of this thing. I want to send you the address where it's located. If I send you the address of where it's located, that means that you can then go to that address and make a change, even though that variable is in my function and not yours. So how does this work? Let's say I've got something called the price of coffee, right? So this is a specific price inside of main. I've got some weird tax function that just gives me the amount of tax on an item, but I don't know what it is. It just takes a generic price. But if instead of passing by value, I pass by reference, in other words, the price of coffee is right now pointing to a specific memory location, and it has a value in it of $11.99, and then I pass that address to the tax item function. The tax item function could use that address. Like, yeah, I'm getting a copy of the address, but that address is pointing specifically to a location. If I make any changes to the price in tax item, when I go back into main, those changes are going to be real. Like, you actually changed the location, the value at that location. So it's going to be changed for main as well. That's the idea of pass by reference. So here, the exact same thing, except instead of passing values, we're going to use pointers. So you notice swap has been completely rewritten. I now have an integer pointer A and an integer pointer B. And then I have to use these different pointers to sort of flip stuff back and forth. That means that when I call the function, I can't actually just send the variables. I have to send the address of those variables, so I use the ampersands. This is kind of what you would expect, based on what your knowledge of pointers are. This is what you would expect, how you would expect it to work, right? Swap takes two pointers. I have to pass two addresses, and then you make the swaps with those pointers, and then that's actually going to solve the problem, just by dereferencing the values and copying them and moving stuff over. Make sense? So that is my swap function, which now works. The problem is, boy, that's a lot of asterisks and ampersands, and it doesn't really work. Like now I have to change the way I think about stuff. When I call swap, I actually have to send an address. Now, by the way, there's an argument that that's actually the way you want to do it, that the person calling a function should acknowledge that, hey, by the way, my function, or these values may get changed by your function. But that's an argument for another day. Right now, this all looks messy. C++ has a slightly easier way to do it, and it's called a reference. So, a pointer is a separate variable that holds an address. But when you create a variable like n, so int n equals 42, what is n? Like, that name doesn't exist anywhere in the computer. It's just a memory offset that when the compiler is doing its work, it kind of knows that, oh yeah, so it's like, 18 bytes up from this location. That's kind of where we're going to do the thing. The name n isn't actually used in machine code. It's just a way of sort of having a reference to a particular location in memory. And so C++ has the ability for you to create multiple references, sometimes called aliases, which I guess maybe if you're on a Mac machine, you used to be able to right-click and create an alias. Anyway, it's fine. Point being, you may have had a computer experience where you created aliases for like other programs that you just wanted to place out there. I think in Windows they call them shortcuts. Regardless, the idea here is that we're creating an alias for n called ref. Ref is a reference. It's actually a lot like the original n. It's just a symbol that's being used to refer to a particular location. But it is not a separate variable. It doesn't take up more memory. It's just, I'm giving n a second name, and that second name might actually, like, see the way that I'm assigning that value, right? I'm just taking that name, that alias, ref, and I'm assigning it n, which is just telling the compiler, hey, by the way, ref and n are referring to the same location in memory. But you're not actually going to create these as separate variables. It's just that place has two names now, n and ref. And because of the timing of the way we pass things into a function where we're assigning that value, we can use that to our advantage. So here, I have the exact same code I did before, but it looks a lot cleaner. If you notice, swap now says it takes two int aliases. The swap function itself, the argument, or sorry, not the argument list, the parameter list in the swap implementation has two aliases, right? In other words, A and B are now going to be references that are going to point, or not point, they're not pointers, they're going to just refer to, they're going to have like the same, they're going to be the same location as something that gets assigned to them. Which means if I send the names of two variables, those aliases will then point to the locations of those two variables. So you notice back in main, well, you'll notice that inside of swap, I don't have to do any pointers. I'm back to just using regular variables like I would for anything else because they're aliases. They have, they are a variable name. Just like I would use a variable name in main, I now have access to those locations in swap, right? Because you pass me X and Y, but yeah, I'm using them like a normal variable. And you'll notice that inside of main, when I call swap, I just send X and Y, which is kind of what I would expect to do. I'm sending X and Y, and you're swapping the two. Again, the problem with this might be that in main, I don't have any way of knowing whether or not your variable or your function is actually going to change the original values. That might cause me some issues at some point. Other languages find a way of, denoting that, like you have to acknowledge that you're sending something, like Swift has this in-out keyword that they use when you try and pass stuff by reference. But regardless, it's at least a little bit cleaner, and this is actually the more C++ way to solve the problem, using aliases rather than pointers. Why is this important? Why does it matter if you pass by reference or you pass by value? I've got a bunch of examples up here, but the idea is partially, if you're wanting to create, right now we're dealing with integers, right? It probably doesn't matter because the size of an integer is probably the same as the size of an address, thereabout. But when you start having objects that are much larger, passing by value, like trying to copy those things would just be too much. Picture, a game with, some model with, thousands of polygons and some high bitmap, wrap around it. It's just, you don't want to have to copy that stuff. The other thing is, sometimes you want to actually make a change to the original object and not to a copy of the object. So if I'm using, objects to, let's say, implement a hospital management system, right? I don't want you to prescribe drugs to a copy of a patient. I want you to prescribe drugs to the original patient, right? Like creating a copy of something, or creating a copy of like, oh, here's this person's, prescriptions array. Like, I don't want you making changes to a copy of that array. I want you making changes to the original array that exists inside that patient. Otherwise, they may not get the drugs that they need because it's not where am I referencing stuff? I've now got multiple copies of things. But also, we have the possibility of you prescribing drugs that interact with each other, or multiply, prescribing drugs that, like could lead to an overdose or something. Sometimes you want to edit the original object and not a copy of the object, and so that's a good case where you'd want to pass by reference. Other languages make it sort of automatic that when you're dealing with objects, you're always passing by reference. You don't get a choice. This is Java, right? Java doesn't allow you the choice. C++, by the way, does allow you the choice, which makes it great. It's the reason why these are the languages that are, for the most part, you would use to write system software, because you need to have that sort of fine-tuned ability to make these decisions. Now, moving on from pointers, let's talk about structures, or structs, sort of use the simple term. Structs are inherited from C. They're a way of sort of binding bits of data together into a larger package. So using the analogy that, a variable is like a box that can hold a value, and if that's the case, then an array is like one of those pill boxes with all the days of the week, because then, they're indexed by day of the week instead of numbers. We use numbers, but so they're boxes that are all sort of stuck together. So I can say, oh, I just want to go to the Tuesday box in this particular array. Structures are a lot like bento boxes, right? Why am I using Japanese? It doesn't help. They're like TV dinner trays, right? Or frozen meal trays. TV dinners, I'm aging myself. Point being, right? A TV dinner tray is a structure that is set up. It holds a main entree, it holds a starchy thing, it holds a vegetable, and sometimes in the center they had a little place for a dessert, right? What you got depended on the thing. Could be enchiladas, rice, beans, and some sort of like corn cake, or it could be turkey with whatever that little stuffing stuff was underneath it, and some mashed potatoes over here, and some peas over here, and like a cherry cobbler, right? The structure always held the same thing. The types that it held were entree, starch, vegetable, dessert in those particular locations. But it was treated as one package, right? It's a thing. Structures will give us a way of creating new types in our language, right? So I can take, it's hard to represent something with just a string, right? What's a string? Like, we're going to begin to start thinking of bigger, I'm going to say objects, but we're not talking about objects yet, although I will say in C++, structures and objects are almost identical in the way they're implemented. There's one small change, but it won't make sense until we talk about objects later on. It has to do with private and public members. But, right, structures, basically objects, and these structures are created up of different data types that you've already used, right? Those data types become members in the overall structure that I'm trying to create, and that structure becomes a new type in my class, a new type of variable that I can create. They're not really variables, they're structures, and their members are variables, but you can think of them like a variable, right? I want to create a new student, I want to create a new patient, I want to create a new whatever. So here's where it can kind of get a little confusing. Structures can actually contain arrays. Like, one of the members could be an array of strings. You can actually create an array of structures, right? So I could have an array of students. I might create a struct that represents a class, and a class has one of its members be an array of students. And those students you can picture how this gets really complicated, and that sounds like it would be a bad thing, but it's not, because it sounds like because you can create things that are complex, that allows you to model problems in the real world, right? The relationship between a patient and a hospital, and a hospital room, and a prescription, and a drug, and a doctor, and all this stuff can get really, really complicated. And so having the ability to actually model that stuff is important. So yeah, you can have arrays of structures that have arrays inside of them that have different structures inside of those arrays, and all sorts of more complicated solutions. But let's get to how you declare one. So here I'm going to define a new type in my program. I'm going to put this before main, up with my declarations, like my function declarations, because chances are things are going to need. In fact, I'm probably going to put it before my function declarations because some of those function declarations might actually use the struct. Over time, we have a separate header file, but if you put it before your function declarations, you're going to be all set when it comes time to create a header file. So yeah, I'm going to try and create a structure called an album. And what is an album? Well, an album would actually probably contain also an array of strings called tracks, because you've got different songs on the album. Let's keep it simple. An album for me is going to be a title, an artist, and a year. That's it. You could put in a genre, but what does genre mean anyway? Who's pop? What does alternative mean these days? I have no idea. So, title, artist, year, right? So to do that, I can declare this structure, struct album, and then inside of curly braces, I can define all the members. The members that I have are string title, string artist, int year, all right? Those three variables inside of that struct, that means that every time I create an album, right? When I create a variable of type album, I'm creating a variable that has enough space to hold two strings and an int. It's much bigger than a normal variable. It's like three variables stuck together. And based on where their locations are, we'll know kind of where things are located, or the compiler will. We just are actually going to call them by names because those members have names, right? Every album has a title. Every album has an artist. Every album has a year. And I can create as many albums as I want, and they will all have those three variables inside of them. It's like one object that has three things in it, like a TV dinner tray. So if I want to create a variable of type album, how do I do it? Same way I create an int. Type, name, done. Album, favorite album, semicolon. I have created a variable, I've created a struct of type album, right? And that album, favorite album, has inside of it spaces to hold a title, an artist, and a year. How do I get to those members? I use dot notation. So dot notation is that member operator. That dot will allow me to access a specific field. Java calls them fields. We'll just call them members, whatever. But inside of that struct. So album, favorite album dot title equals the Black Parade. So I took that string and I stuck it into that struct. Favorite album dot artist equals My Chemical Romance. Slide that in. Favorite album dot year is equal to 2006. We put that in there. I can also access it on the other side, where here I've got int years ago equals 2020, which happens to be the year that this is being recorded. Boy, what a year, huh? But regardless, 2020 minus favorite album dot year, that will do some math, because favorite album dot year is going to reference whatever the year is inside of the favorite album struct, which happens to be 2006. So that was 14 years ago, which feels like so long. It's fine. But anyway, there we go. Structured members, you want to access the member, you just use dot notation. You can also initialize, by the way. You just have to, when you initialize, you have to remember the order. So for instance, we declared our struct as title, artist, year. So that means that those two strings, right, American Idiot and Green Day for my album Close Second, they have to go in order. If you don't put them in order, then you're going to have Green Day as the title and artist is American Idiot, which, could be a thing, but it isn't. And then obviously the int would have to be in the third position because that's the third thing that we declared when we declare the structure. So initialization works if you kind of know where things are coming, but again, like most things with initialization, it's helpful for like testing purposes as you're writing code. But where are these values coming from? Chances are you're going to be getting them from somewhere. And so being able to initialize stuff like that isn't always the easiest. Again, good argument. If you wanted to declare something with empty strings and zeros for all the int values, you had some like good default values, you might, when you create something, put in the default values through initialization. Now, we're going to kind of combine these things a bit, which is to say, C++ allows you to create variables at compile time. Compile time means as you're programming, right? Like I can create an integer in. I can create an album, favorite album, right? I can do whatever I want. These all happen at compile time. I can create the variables, they exist, bam, they're there. But the problem with that is, how do I know how many albums you have in your collection? How many friends do you have on Facebook? How many likes is that post going to get? Like, I don't know. Like, I need to find another way of doing this, given that what am I going to create an array that has like, thousands of potential things, because I have to, use the same array for your post of your, child or something, and that has to compete with, whatever Billie Eilish is doing this weekend. Like, no, she needs millions of likes, and you just probably need a few dozen, right? I don't know, you may be really popular. Point being, I don't know how much memory I'm actually going to need for a lot of these objects. And beyond that, like, because I don't know that, I don't want to waste memory by assuming too much or making it so that, Billie Eilish gets topped out at 1,000 likes. So what I can do is I can create variables at runtime. And to do that programmatically, to create dynamic memory, it's a lot harder. But your computer has a place, as you run a program, in RAM called the heap, or sometimes called the free store, but I usually say the heap. And it's where you can store objects and variables and other things, right? You can do it dynamically at runtime. Just say, hey, I want to create a variable up here. But the problem is you're not going to have any ability to, like, I can't name it, right? How do you name a variable you don't know is going to exist at the time that you're programming, right? So I need to have a way of referencing it. So what I could do, right, is I could somehow get the address of it, because I could probably programmatically find a way to store the addresses for something as it grows, right? And so that's the idea of dynamic memory. I'm going to, at runtime, when somebody's actually using your application, I'm going to create a variable or an object or whatever, or a struct, right? We have structs now, no objects yet, but they're coming, right? And I can place it into the heap, right? What I'm going to get back is a pointer, the address where that thing just got stored, which I should probably hold on to. It's kind of important. So the keyword we're going to use for all of this is called new. If I want to create a new album programmatically at runtime, what I can do is just say album pointer A or whatever equals new album, and that creates a new album. You can picture this happening maybe in a function or something. Somebody adds a new album, and then eventually I somehow pass that address back to somewhere where it gets stored into like a vector or something. We don't have vectors yet, but we'll get there. Or I could create a linked list, which we'll learn about in another class, unless I get really crazy. You could create a linked list and have unlimited amount of storage to store as many albums as you want. But here the idea is I'm creating an album at runtime. That album now is in the heap. So when you create a variable inside of a function, the second that function finishes executing, that variable goes away. This variable doesn't go away. It's stored somewhere else. It persists beyond the end of that function, which means you can still reference it from other functions when they start, needing to have access. It's a way of doing it, right? But the problem is, of course, if at any point in time I lose the address, right? I just decide to get rid of A or change the value of A. Now I no longer have a way of referencing that object, which is a problem because it creates what we call a memory leak. I'm using memory for objects, or for variables, I should say, or structs, that I no longer have access to and I can't actually use. So keeping track of that is important. If you no longer need something and you're going to switch the value of that pointer, that's fine. You just have to delete the thing that you had it at before you switch the value. Otherwise, you're going to be using memory that you're not actually using. And that's going to increase the memory footprint of your application and potentially cause it to run slower, yada, yada, yada. So now, how do I access members when I'm using a pointer? Well, it would make sense that if I use the member operator, the dot, on a type that's kind of like a variable, like an album, then I would want to dereference the album and then use the dot, which does work. Absolutely. The problem is the dot has a higher order of operations. It takes precedence over the star. So you're not going to dereference A and then access the member. You're going to dereference the member at A. Well, title is not a pointer, so this is not going to work. What I have to do then is put parentheses around the star A, and then once I'm done dereferencing, then I can do dot title. And that, by the way, does actually work. That's method one. That's the intuitive way of doing it, the way you would think to do it. And you can do it that way. People will probably make fun of you eventually, but it's fine. C++ has a shortcut that does both. It dereferences and accesses the member all in one thing. It's the arrow operator. So the arrow operator, which is actually two symbols, it's hyphen greater, greater than, hyphen greater than, put together, kind of look like a little wonky arrow. It kind of depends on the font, but some fonts it'll look better. Regardless, that arrow operator will dereference the struct and then access the member afterwards. So here I created a new album. I set the title to 10, perfectly valid way of doing it. I set the artist to Pearl Jam. That's actually the better way of doing it, in the way that's not going to get you made fun of in the break room, eventually. If you know C++, arrows, whenever there's a pointer to the left, use an arrow. Whenever there's a variable name to the left, use a dot. Now, I mentioned, if you create something, you lose the reference to it, you're going to need to delete it yourself. How do you delete something? You just say delete and give the name of the pointer that you want to delete the thing that it's at. And because pointers always know what type of thing they're pointing at, it'll know exactly how much memory to delete from that point up so that it's released and you don't have to worry about creating a memory leak. So in C++, because C++ does not do garbage collection, if you create a object, it is your responsibility to delete that object, right? At least if you're doing it dynamically. If you're doing it just normally inside of a function, no problem. As soon as that function closes, then those objects get deleted. But if you're going to use the heap, you're going to shove stuff up there, it's your job to go clean it out, right? The heap is basically the break room refrigerator for your program. If you put the Chinese in there, you've got to delete the Chinese before it goes bad. Terrible analogy, but you know what I mean. By the way, you can also declare an array of not objects, they're structs. They're almost identical in C++, but I think of them as different things. And we'll talk about that when we talk about objects. So you can create an array of these things just by using this sort of array notation. Product pointer p equals new product 12. That means I'm going to create enough memory to store 12 different products. And the first one I'm going to reference with p, right? So it's easy. Created a new type, new whatever, 12 products. First one's going to be referenced by p. If I want to delete all 12 of those objects, I just do delete the array at p. Because p knows how many of those products, how many of those structs that we have there, it'll know how much memory to delete from that point up, right? These are all sort of contiguous, using fancy words. These are all memory addresses that are touching one another when you create an array. Right, so delete, if you're going to delete an array, use the delete array keyword. Now, I've got a pointer to the first object, but how do I actually float around in between the different objects? Well, as it turns out, pointers are overloaded. We'll talk about operator overloading later, but pointers are overloaded with the plus plus and minus minus operators. So if p is pointing to the first object, I can use p plus plus to advance to the next object in that array, or struct in the array, right? So I can make the first product LaCroix, I can add one, do beard oil, do one of that, avocado, something or other, and then I can use p minus minus to go back an object. So I can advance and retreat in that array just using p plus plus, p minus minus. Whatever your pointer is, you just go back and forth, back and forth. Just make sure that if you're going to delete an array of objects you've declared dynamically in the heap, make sure if you're using p, like either create a different pointer to go traversing around in your array with, and leave P where it is at the beginning. So when you delete from the beginning. Otherwise, if you move up, like just make sure you go back down to the first element before you delete the entire array. I'm covering more concepts than you'll actually use in this week's assignment, but regardless, that's how you would do it if you're dynamically declaring more than one of a type of struct. All right. Last topic, constants. So constants and pointers kind of work a little bit differently. When it's a variable, it's real easy. Constant int n means that it's a constant. You can't change the value of n. Once n is done, it's done. And that's because the constant went before the type. Here with constants and pointers, we've got a couple different options, so we'll talk about them quickly. Because honestly, I don't know that I use it this much. But if I put the const after the type, so int pointer const p, right, then the p is a constant. I have a constant pointer, right? But the variable, the value, is not constant. That means I can change the value of, at that location, but I can't have that pointer point to a different location. The pointer itself is constant, but not the value. If I put the const before the int pointer, then I get the ability to switch the location that I'm pointing to. The pointer is not constant, but the value at that location is constant. So I can't change the value of where the pointer is pointing to, but I can actually move that pointer somewhere else, which at that point I would lose the location, so probably not a good plan. Regardless, if the constant is before the int pointer, you can't change the value, but you can change the location. You can also have a constant type, constant name, in which case you can't change either. Everything is locked down. And that's it. Those are pointers, those are structs. If you have any questions, and I'm sure you will, send me a message on Canvas, and yeah, as always, I'll see you online.